Welcome, my friends. In this video, I'll be discussing section 6.2, which is titled Linear Correlation. The correlation coefficient, represented by the lowercase letter r, describes how strong the relationship is between two variables x and y. R is a unitless measurement between -1 and 1, and relates to a scatterplot. So let's look at a number of different scatterplots and what the value of r would be. So if we have what we would call a weak to moderate positive correlation, which would be an r value of somewhere between 0.2 and 0.6 approximately, then that means as our x variable increases, our y variable tends to increase as well, but it's really not that strong of a relationship. Or on the scatter plot, the straight line fitting the dots is not really that strong of a fit. And if we increase the value of r to maybe 0.6 to 0.8, that would represent a moderate to strong positive correlation. And so we still have the same type of pattern where the straight line fits the dots, but it's just a little bit more of a stronger fit. So now the straight line is closer to most of the dots, or you could say the dots don't stray from the straight line as much as they did in the weak to moderate case. And the closer that the r value gets to 1, the closer the dots are going to be to the line, and the stronger we will describe the correlation. So if we're like 0.8 to 1, we might say this is a strong to perfect positive correlation. At the very extreme, where r is equal to 1, every single dot would fall exactly on the line. Note that we are only talking about the linear correlation coefficient at this time, so these are only going to be representing linear relationships or straight line relationships. If we had some sort of curve, then we would use something else. Okay, we can also have negative relationships, which means as one variable increases, the other one tends to decrease, or vice versa. So if we had a weak to moderate negative correlation, that would be an r value somewhere between maybe -0.2 to -0.6. So that would be indicated by a downward sloping line, and the line would not really fit the dots super well, meaning the dots are quite a bit above and below the line in many cases. And as we get closer and closer now to not +1, but -1, we'll be approaching the stronger negative correlations. So -0.6 to -0.8 might be moderate to strong negative correlation, and -0.8 to -1 would be a strong to perfect negative correlation. So basically, the closer we are to either 1 or -1 is going to be representing a stronger relationship, or where the dots are going to be closer to the line. And the closer we are to 0 is going to be representing a weaker relationship, where the dots stray more from the line. Another way to think about this is on a number line. So the value of r, the correlation coefficient, can go anywhere from -1 all the way up to +1. And at the extremes, we describe that as the perfect correlations, either a perfect negative or perfect positive correlation. Now, these are both perfect correlations, meaning that all the dots would fit exactly on the line. But the difference is this would be a downward sloping line where the two variables go in opposite directions, whereas this would be an upward sloping line where the two variables go in the same direction. And as we get closer and closer to 0, we're going to have the weaker correlations. So here we have strong negative or strong positive, kind of in this range of these numbers. As we get closer and closer to 0, we're going to have weaker and weaker correlation. So we have weak negative or weak positive. And finally, at 0, we have no correlation. And we'll take a look at what it means to have no correlation here in the next few slides. Okay, I fixed that end there. That was bothering me. Okay, so we can consider the two attributes of the correlation coefficient r. So there's two things you consider whenever you are kind of interpreting or describing the correlation coefficient. So first thing you should consider is the sign, meaning r can be either positive or negative. A positive value for the correlation coefficient r means that the two variables basically go in the same direction. So if x increases, then y is going to tend to also increase. And a negative value of r is going to mean that the two variables go in the opposite direction. So as one variable increases, the other one is going to tend to decrease. Note that we are not saying there is a causal relationship between our two variables. We're not saying that x is causing y to increase or decrease. We're just saying that there tends to be this pattern here. Whether or not it is causal or maybe there's a lurking variable, we don't really know based on just the correlation coefficient. The second attribute we should consider is the strength of the relationship. So not only do we want to know about the sign, we also want to know about the strength. So the strength is going to be stronger the closer we are to either 1 or -1. So a value of r that's close to 1 or -1 is going to indicate a strong relationship. And that means that a straight line would fit the dots quite well on a scatterplot. A value closer to 0 is going to indicate a weaker relationship, where a straight line is not going to fit the dots very well on a scatter plot. Now, just because you have a correlation that's 0 or close to 0 doesn't necessarily mean there's no relationship at all, because remember, we're only considering the linear correlation here in this section. So here are a couple of examples of scatter plots that would have some sort of relationship, potentially, but would have a linear correlation coefficient that is 0 or close to 0. Now, the very first one does not have any relationship at all, which is really the reason why there is no linear correlation. Really, the question you want to ask yourself is there a logical way to fit a straight line through all the dots in your data? And how would you draw the straight line? Would you draw it like this, or would you draw it like this? There is not really any logical way to draw that straight line, which is indicating that the correlation coefficient is going to be 0 or close to 0. Now, in the second picture here, there is a relationship. It's kind of like a quadratic relationship, or you might call this like a x squared type relationship, or a parabola. But it's not a linear relationship. So there's not really a logical way to draw a straight line through this one either, right? But it doesn't mean there's no relationship whatsoever. There is a relationship. It's just not a linear one. And same kind of idea with this one. There's some sort of relationship here, but how would you draw the straight line? There's not really a logical way to draw one straight line here. This is more like a trigonometric function, like a sine or cosine is kind of what this looks like. So sometimes things that oscillate over time or something could maybe look something like this, right? So even though there might be a relationship between your variables, it could be the case that your relationship is not linear. So this further adds to the argument that you should always be graphing your data before you do the analysis, because you might be trying to fit a linear relationship to something that's clearly not linear. Okay, so there is a problem with outliers, in that outliers can sometimes have a dramatic impact on the correlation coefficient. So once again, you should always be creating a scatter plot of your data before finding the correlation coefficient. Now, in some cases, it will have a dramatic impact, and in some cases, it will not. So let's look at a couple of examples of different cases here. So we have two different scatter plots. One has an outlier over here, both in terms of x and y, but the outlier seems to kind of fit the pattern, right? So if we just kind of connected this with a straight line, that outlier, it is an outlier, but it kind of fits the pattern of the rest of the dots. And this one doesn't have an outlier on the left. Well, it turns out that the correlation coefficient for the left graph is negative 0.846, and the one on the right graph is negative 0.930. So what effect did the outlier have? Well, the outlier tended, in this case, to actually strengthen the correlation, made it a little bit closer to -1. So we would say in this case, it really did not have a dramatic impact. It really just kind of strengthened the relationship here, because that outlier really was in the pattern of the other dots that were already there, right? So outliers in x and y that follow the pattern will strengthen the value of r, but not really have that substantial of an impact. Let's look at another example. So here's another example where we don't really have much of a correlation at all in the first case, and then we introduce this outlier up here, which is an outlier in terms of y, but not so much in terms of x. So it turns out the correlation in the first case is very, very low. We would say that it is negative 0.081, or that's a very, very weak to no correlation there, right? Whereas the one on the right is even worse. So it's negative 0.008, so very, very, very close to 0. But this one is already so weak to begin with, so the introduction of the outlier didn't really change things all too much, right? So if there's already close to no linear correlation, then the outlier also might not really have that much of an impact, right? But let's look at one more case here. So in this case, we have some identifiable pattern, like a negative relationship here, and we have an outlier that completely goes against that pattern. So we have an outlier not really in terms of y, but it is in terms of x, and it's also not fitting the pattern whatsoever, right? The value should be like way down here if it was fitting the pattern, right? So the correlation coefficient on the left one is negative 0.701, and the correlation here, can you believe it, is actually negative 0.179. So that 1 point had this ridiculously crazy impact on the correlation, right? Right here, it was a moderate to strong negative correlation, and here we're almost in like the no correlation zone. But obviously, there is some kind of correlation here. We just have like one bad point, and so you might want to kind of research into what made that point so much different from the rest, and maybe consider doing the analysis with and without that outlier to see how it kind of changes things, right? So outliers that break that straight line pattern can have a substantial impact on the value of the correlation coefficient. So once again, another reason why you should always be graphing your data and not necessarily just looking at the correlation to tell you about your scatter plot. All right, that's all I wanted to talk about in this video related to the correlation coefficient, so I will see you in the next one.